right, we're going to talk today about Chapter 1, Part 5. Title is Parent Functions and Transformations. So first, some definitions. First of all, a parent function is a particularly important mathematical function that is used to model a lot of different real-life situations or is given significance for some other reason mathematically. So let's just say an important function. From which many others are derived. And then a constant function. So this is the function f of x equals k, where k is some constant value. And the graph is going to look like this. So you got some line k, like so, has a zero slope. And then the zero function is a special type of constant function where f of x equals 0. And it's just the x-axis. Like so. The identity function, so that's going to be f of x equals x. So this takes the input and just gives you the same thing as the output. It's going to look like this. Then I've got the quadratic function, and the parent function is like this, f of x equals x squared. Once again, you've probably seen this graph before, but this parabola shape. Some people call it a ball shape. The cubic function is f of x equals x cubed. And it's a little different. Looks like this. So the square root function is going to be f of x equals the square root of x. And its graph's going to look like this. Finally, the reciprocal function, which is f of x equals 1 over x. This is the most complicated graph on this list. But it looks something like this. And that's the reciprocal function. So these are considered parent functions. Now there's a couple others we'll use, and I'll go ahead and talk about them briefly here. There's the absolute value function. And it looks like this. And then the graph has this distinctive V shape, like so. And then also we'll talk about today the step function, STEP, which probably includes a mathematical operation you've never seen. Hey, buddy, got some if you need. So this is probably something you guys haven't seen before. And it's called the step function. And what it does is it throws away any fractional part of the input. So if I plug in 6.8, it becomes 6. 0. So it takes away any fractional part and goes down to the next, the integer to the left on the number line. So it throws away any fractional part. In other words, it always rounds down. which creates kind of a funny graph. So I'll show you what that looks like. You have these steps, like so. So that's a pretty interesting looking graph. That's for the step function. Okay, so your book has a list of these and some interesting things about them. Feel free to look through there. Okay, so describe the characteristics of the graph of the parent function f of x equals 1 over x. So we'll start with the graph. Remember that I told you the graph looked kind of like this. So graphical analysis is going to be important. And we're asked to find the domain range, intercepts, symmetry, continuity in behavior, and intervals of behavior. Okay, so first of all, the domain. If I look, I see that there is one excluded value on the domain. So the domain is x such that x is not equal to 0. Everything else works. Everything else will be defined, but at 0, I'll have division by 0, and it will not be part of the domain. The range is the same. So every y value is also valid with the exception of 0. The intercepts, it never touches either axis. So these don't exist. I'm going to put NA for not applicable. The symmetry, it has odd symmetry. In other words, f of negative x is equal to negative f of x. Continuity, it has a discontinuous point at 0. So it's discontinuous at x equals 0, and it is an infinite type of discontinuity. The end behavior. So this will be two limits. The limit as x goes to negative infinity of f of x, and that's going to be 0. You see how as we go further and further out to the left, the graph would get closer and closer to 0. And then the limit as x goes to positive infinity of f of x also equals 0. You'll see the same behavior as we go out to the right, just approaching from a different direction. And then intervals. So it's got two intervals. First of all, negative infinity to 0, where it is increasing, and then 0 to infinity, on which it is decreasing. So there's our analysis of 1 over x. Okay, so here's one for you. Do the same thing with x squared. Pause the video, see if you can figure out all these characteristics, and then come back and we'll see if you were right. Okay, so f of x equals x squared. The graph, remember, it's this bowl shape. Kind of got a little wonky over here. Let me see if I can salvage that. There we go, a little bit. So the bowl shape looks something like that. It does include the origin here. So first of all, the domain is going to be x such that x is a real number. In other words, everything. There is no x value that is excluded from the domain. Any x value will work as long as it's a real number. The range, y such that, now this is a little trickier. Y is greater than or equal to 0. it's undefined below 0. So y has to be greater than or equal to 0. Intercepts. So this has an x-intercept at 0 and a y-intercept at 0. Symmetry. This has even symmetry, in other words, symmetry to the y-axis. And it's because f of negative x always equals f of x. You can see if I rotate this around the y-axis, I get a symmetric situation. So even, and it can be proven via the f of negative x equals f of x. Continuity. This function is continuous. In other words, you could graph it without picking your pencil up. You'd never have to pick your pencil up, no matter which portion of the graph that you were drawing. In behavior. So in this case, the limit as x goes to negative infinity of f of x, and the limit as x goes to positive infinity of f of x, in both cases, this will be positive infinity, because you see it goes up, up, up without bound in both directions. And intervals of behavior. Once again, we have two intervals here. We have from negative infinity to 0, and then from 0 to infinity. It's decreasing on this left interval, increasing on this right interval. So let's talk about translations. First of all, vertical translations. That's where I just shift the graph up or down. So what I'm going to do is add a factor k to the function, and if it is positive, it shifts the graph up. If it's negative, it's going to shift the graph down. So you'll see two examples here. Now, horizontal translations, these are not as intuitive. So you should know that input effectors often behave the opposite of the way you would expect them to. Output effectors, you probably could have predicted this. Input effectors are a little different. So here if I subtract h, so notice this subtraction symbol. Over here they add, so that's kind of an inconsistency, but they subtract here to account for that counterintuitive nature. So if I add something to the input, it's going to go left. If I subtract something from the input, it's going to go right. You probably need to see a couple examples to understand that. Anyway, again, if I add something to the input, it goes left. If I subtract something, it goes right. The opposite of what you would expect it to do. So let's use the graph of f of x equals x cubed to graph x cubed minus 2. So f of x equals x cubed and g of x equals x cubed minus 2. So first of all, x cubed, that parent graph. So we use these 3 points to kind of guide me here. So all this minus 2 is going to do is translate those points 2 units downward. Like so. And we can graph this on the calculator. And you'll see a similar shape. So if I go to y equals, clear out whatever's there, punch in x cubed, and then below that, x cubed minus 2. And let's zoom 6 so we get the standard window. It'll be bigger than the window you see here. But you'll see a similar shape to what I have there. And if I set my window to go from -3 to 3, and then -3 to 3, which is what I graphed over here, you'll see it's more consistent with what I had drawn. Okay. So what if we had an input effector? And again, I told you, these behave the opposite of the way you would expect. So I have f of x equals x cubed, and g of x equals x minus 1 cubed. Well, this input effector, it's minus 1, so it's going to move us 1 unit to the right. So again, input effectors behave often the opposite of your instinct. So y equals x cubed includes these 3 points. And it goes around them like so. So we just move all those points to the right one. We'll have this graph. And again, we can use our calculator to confirm. All right. So here we've got both things happening simultaneously. So in this case, we're going to go 1 unit to the right and then 2 units down. So here's our points for y equals x cubed. And so we'll take those points and go 1 unit to the right and 2 units down. Like so. And then we'll graph the same shape around. Roughly the same shape. Nobody's perfect if you're drawing it by hand, so it might look a little bit imperfect. So if I add 2 to, or subtract 2 rather from the end here, I have the right graph. Okay. So here's one for you. See if you can figure this out. Pause the video and then come back and see if you're right. Okay, so starting out with f of x equals x squared. I like to use a couple points. So this So f of x equals x squared includes the points -2, +4, -1, +1, 0, 0, 1, 1, and 2, 4. So you remember the shape, the parabola shape. So there's f of x equals x squared. Now here, we're going to go 2 units right, and then 1 unit down. So I take these points and I go 2 units to the right and 1 unit down. 2 units to the right and 1 unit down. 2 units to the right and 1 unit down. 2 to the right and 1 down. And then finally 2 to the right and 1 down. So our new, should probably use something other than red there. Let's use the green. So there's our g of x. And we'll use the calculator once again just to make sure we're right. So x squared is our parent function. And we want x minus 2 squared and then minus 1. Yep, there we go. And I've got an extra unit on my graph is why it's a little different. Okay, so reflections in the coordinate axes. If I multiply the output by -1, it's going to reflect over the x-axis, as you see here. So reflection over the x-axis is when you multiply the output by -1. Now, if I multiply the input by -1, that's going to reflect us around the y-axis. So reflection in the x-axis occurs when I multiply the output by -1, and reflection in the y-axis occurs when I multiply the input by -1. This is for the graph. So describe how the graphs of f of x equals the square root of x and g of x are related, and then write an equation for g of x. So this is kind of tricky. Here they just give us the graph, and they ask us to figure out what g of x looks like. So g of x, if I start with f of x equals the square root of x, I see over here I'm up 1 unit. So the way that would look is the square root of x plus 1. That one's pretty easy. And then here's another one. So quite a bit more complicated. Here we're moved. So we've gone left 1. So I know I need to add 1 to the input. And then we're flipped over the x-axis. So g of x, in this case, is going to equal the square root of x plus 1, and then we need to multiply that by -1. So let me give myself a little room here. So equals, and then negative. Let's see if that looks like what we got there. So square, well, should do my negative first. Square root of x plus 1. Okay. Yeah. So the left one was accomplished by adding 1 to the input. The flipped over the x-axis, I multiply the output, in other words, the whole function, by a negative. So here's one for you. Pause the video and do this work, and then come back and see if you got it right. Okay, so describe how the graphs of x cubed, which is here, and this graph are related. Well, clearly, for our vertex is moved down 1, 2, 3 units. Can't really tell if anything else is going on, but I'm going to say this is x cubed minus 3, because it's shifted downward 3 units. Okay, vertical dilations and horizontal dilations. So once again, the input effectors are going to behave weirdly, but the output effectors are just like you would expect them to. If you multiply it by a number greater than 1, it expands. If you multiply it by a number between 0 and 1, a fraction, it's going to compress. So expanding vertically, think about it this way. If it were like 2 ropes you had suspended, you pull it up tighter. So that's a vertical expansion. And then a vertical compression, if I relaxed those 2 cords and let them ease towards the ground, it would do like this. So that's a vertical compression in the second diagram. And then on the right, the horizontal dilations. So if you have a value greater than 1, it compresses. Once again, it behaves the opposite of the way you'd expect. Compresses horizontally if it's greater than 1. And if it's a fraction, in other words, between 0 and 1, it will expand horizontally. So notice the analogous situation between these 2. Okay, so here we have the parent, the g of x equals 3 over x. It says identify the parent function. So that's going to be f of x equals 1 over x, the reciprocal function. And describe how the graphs are related. Then graph them on the same axis. So this is f of x times 3. So in other words, we have had a vertical dilation. We've multiplied the output by a value greater than 1, which is a vertical expansion. So this is a vertical expansion, or I just often call it a vertical stretch. So it's vertically stretched up tight. We'll graph it on the calculator because this one will be a little trickier to graph well by hand. So 1 over x is our parent function. And in your calculator, you can change the way a graph represents. So we'll make the parent function normal size. And then if you hit enter right here, it makes that line fat. So you can have a fat graph. Makes it easier to distinguish between the two. And we'll zoom 6 so that we have a standard window. There's the normal, 1 over x. And there's the fat line. You see how it's expanded just a bit vertically, a little further away from the axis than the original function. All right. Now let's talk about this one. It says, identify the parent function of g of x equals negative the absolute value of 4x. And that's going to be f of x equals the absolute value of x. And the graphs are going to be related. First of all, we've got to flip over the x. And then we've got a horizontal compression. So remember that when I multiply the input by a value greater than 1, it compresses it. Again, that behavior that you wouldn't expect. So once again, we'll use the calculator to graph these. So if I go to math, and then I go over to the number tab, the first option is ABS, that's the absolute value function. So I'll do the absolute value of x, and then as a fat line, I'll do negative, and then the absolute value of 4x, like so. And then we'll graph those. So there's the original, and there's the modified version. Flipped over the x and horizontally compressed. So here's one for you. Pause the video, work through this one, and then come back and see if you're right. Okay, so negative 0.5x cubed. And the parent function, of course, is going to be x cubed. So we've got to flip over the x, and then a horizontal stretch. So let's use the calculator again just to save ourselves some time. So if I clear out whatever I got here, I'll go x cubed, and then negative 0.5 times x cubed. So there's the original, and there's the modified version. Once again, I'll go here and make it fat so it's distinct. So original f of x, and then here comes g of x. Flipped over the x-axis and then horizontally stretched. So a piecewise defined function. These are kind of fun to graph. They're a little bit of a challenge. Let's use a really good graph here instead of my hand drawn ones. So we've got 3 portions of the domain here, and then 3 expressions. First of all, let's graph this leftmost, which is if x is less than 0. And so we'll graph this one in green. It's the absolute value of x plus 2. Let's get a couple points. First of all, the vertex of this is going to be at negative 2. So we definitely want to graph negative 2. I'll make a little table here of x's and f of x's. Let's go negative 3, negative 2, and negative 1. That will capture the vertex of this absolute value portion. So if I plug in negative 3 plus 2 is negative 1, and then the absolute value of that is positive 1. Negative 2 plus 2 is 0, the absolute value of 0 is 0. And then negative 1 plus 2 is positive 1, absolute value of 1 is 1. So there's 3 points that are going to help me graph this part. If I go to negative 3 and then up to 1, I'll have this point. Negative 2, 0 is here, and then negative 1, 1 is here. And I know it's going to go up 1 over 1 and come to this point, but I need to make that an open circle. So that's kind of hard to do. Maybe if I choose a finer pen here. There we go. And then the graph is going to go like this, on and on forever out to the left. So there's the first part. Now let's do the second part. So that's between 0 and 2, including. So we'll go 0, 1, 2. So plugging in 0 here into the middle expression, the absolute value of 0 is 0, minus 2 is negative 2. Plugging in 1, the absolute value of 1 is 1. 1 minus 2 is negative 1. And then plugging in 2, the absolute value of 2 is 2. 2 minus 2 is 0. So there are 3 points for this middle part. So that's going to be 0, negative 2, 1, negative 1, and 2, 0. And remember, we're including the bounds here because it's or equal to. So those are closed dots in this case. And then finally, a couple points here. So let's do, first of all, let's see what it would look like at 2. It's going to be an open circle there. And then we'll plug in 3. Well, actually, that wouldn't be a great choice because it wouldn't. Yeah, it would. Okay. Yeah, it would be a perfect square. Okay, so 2 minus 2 is 0. The square root of 0 is 0. 0 plus 2 is 2. So we've got an open circle here at 2, 2. And then 3. 3 minus 2 is 1. Square root of 1 is 1. 1 plus 2 is 3. So it's going to come over like that. And then it's going to act just like the square root function, like so. So there is that piecewise function. And I graphed this first one in green, the second one in black, and the third one in blue. All right, moving on. There's the book's representation of that same graph. So here's one for you. Graph this one and pause video, graph this one, come back, see if you're right. Okay. So, let's see. We'll just make a rough, quick graph here. So x plus 1 squared if x is less than or equal to negative 1. Couple points here on to do it. So if I go, so this will be x's, this will be f(x)'s. So if I plug in, let's say negative 3 and then negative 1. So negative 3 plus 1 is negative 2. Negative 2 squared is 4. And then negative 1 plus 1 is 0. 0 squared is 0. So I know it's going to be negative 3, positive 4. So this point. And then negative 1 is 0. Open circle there. So it's kind of be quadratic like so. And then x squared minus 2 if it's between negative 1 and 2. So this is going to be a closed dot because it's included here. Negative 1, 0, 1. We'll do those real quick. Negative 1 squared is positive 1. Minus 2 is minus 1. 0 squared is 0. Minus 2 is minus 2. And then 1 squared is 1. Minus 2 is negative 1 again. So negative 1, negative 1. So this, and it's a closed dot this time. 0, negative 2. 1, negative 1. So this little horseshoe shape down here is from that middle part. And then the square root of x minus 2 if x is, and actually this will go on. I need to plug in one more value here. So 2 squared is 4, minus 2 is 2. So I need to put the point 2, 2 on as well. All right, now, square root of x minus 2. If I plug in 2 for that one, will not be included because it's not or equal to. 2 minus 2 is 0, and the square root of 0 is 0. So this point. And then it's going to act just like the square root function from that point forward. So that's a pretty interesting graph, to say the least. Okay, let's talk about example 6, which relates to the transformation of functions. The wild ride roller coaster has a section that is shaped like the function g of x equals negative x squared over 30 plus 10x over 3 minus 100 over 3, where g of x is the vertical distance in yards. The roller coaster track is from the ground, and x is the horizontal distance in yards from the start of the ride. So describe the transformations used. And they don't say graph it, they say just describe the transformation. So let's do that. So we're going from the parent function, f of x equals x squared, to g of x equals negative x squared over 30 plus 10x over 3 minus 100 over 3. So I can see a lot of things going on, but let's look at the graph on the calculator, and that'll help us understand these better. So first of all, x squared, and then with the fat line, again, negative x squared divided by 30 plus 10x divided by 3 minus 100 divided by 3. So this first term, we see it's multiplied by a negative, so that's going to be a flip over the x-axis. The second term is going to relate to a horizontal translation of some sort, and then the third term is going to be a vertical translation of some sort. Let's graph it and see. So original, and we need to zoom out so we can see that. So let's go, I don't know, 0 to 100, and then 0, I'm sorry, because some of that was below the x-axis, negative 100 to 100. Let's see what that looks like. So there's our original, and then here's our modification. So we see that it's flipped over, and then it's horizontally and vertically translated. So reflected in the x, and horizontally translated, and then vertically translated. We could get in and algebraically manipulate this and find out the exact factors, but that goes beyond the scope of this problem. We're just tasked with analyzing the graph and seeing what transformations have taken place, not exactly quantifying them in this case. Okay, so transformations with absolute value. So sometimes if I take the absolute value of a function, everything that was previously negative becomes positive. So the positive values and the zeros are left alone. Everything negative becomes positive if I take the absolute value of the output. If I take the absolute value of the input, then all of the negative x's are going to behave like the positive x's. So it's suddenly going to have y-axis symmetry, and you'll see that here. So what would the graph of g of x equals absolute value of f of x looks like? Well, remember that all the zeros and the positive values will be the same, but all these negative values will become positive. So it'll look like that. And once again, we use our calculator to check ourselves. So I've got x squared minus 4x plus 3. And then here I'm going to have the absolute value of x squared minus 4x plus 3. And if I go over here and change that to a fat line to be more succinct, and I need to zoom standard here. So zoom 6. Original, modified. We see it matches what we had. So what if I modified the input to be the absolute value? Well, in that case, everything to the right of the y-axis would be the same. And then that would be mirrored on the left side like so. So let's start from scratch here because it's going to be a little more complicated to put in. So the absolute value of x squared, and then minus 4 times the absolute value of x plus 3. I believe that'll be right. So there's the original. Then there's the modified version. Once again, I need to go in here and make it a fat line so it's more distinct when it graphs over itself. Original, modified version. Okay. So what I'd like for you guys to do for me, the due date is chapter 1, part 5, page 52, 2 through 18 even. See you next time.